before we get started for today's lecture? All right, sounds good. So let's get started. We're ready to talk about quantum mechanics bounding theory. So in our previous lecture, we talked about the classical bounding theory, where we talk about Lewis-Dot diagram, resonance structure, and etc. So they work great in most cases in organic chemistry, but classical bonding theory have their shortcuts, and that's why we want to talk. We want you to know quantum mechanics bounding theory as well. So one of the failure of classical bonding theory, if you think about it, is oxygen, so O2 molecule. So we can easily draw the Lewis-Dot diagram of oxygen molecule, which is double bond between the two oxygen, both of them are neutral. We should be happy, and looks like all electrons are paired up by just looking at the Lewis-Dot diagram. However, when chemists actually go and take spectroscopy measurements of oxygen molecule, we find out the oxygen molecule is a paramagnetic molecule. So we say that's paramagnetic. Means that it has unpaired electrons in that molecule's, in that molecule bonding. So apparently classical bonding theory is not able to rationalize that paramagnetism that's observed in the oxygen molecule. So with that in hand, again, today we'll be talking about two quantum mechanics bounding theory. This should serve as a review to your 14A classes, but it's been a while, so we want to make sure we're all on the same page here, talking about quantum mechanics bounding theory. The first part, we'll be talking about molecular orbital theory, which is your chapter 1-7 in your textbook. And then we'll be talking about valence bond theory, including hybridization, which is 1-8 on your textbook. All right, so let's get started. Before we talk about any quantum mechanics bounding theories, the first thing we want to know, again, is atomic orbitals. So we went over that review in our lecture 1, where we're trying to make you understand one thing. Atomic orbitals are hydrogen wave functions. These wave functions are mathematical functions people obtain by solving the Schrödinger equation. So the Schrödinger equation has the general form of a Hamiltonian operator acting on the wave function to give you energy times the wave function. So that wave function we're getting by solving the Schrödinger equation for a hydrogen atom is our atomic orbitals. All right, so everything, when we're drawing these atomic orbitals, so that's a 1s, here are the 2p atomic orbitals. When we're drawing them, they look like just simple cartoon, but what they actually are just waves. They are probability waves. It tells you information about where that electron has a high probability to be in space. All right, so this is just what we discussed in our lecture 1. And the two bonding theory we'll be talking about are molecular orbital bonding theory and then the valence bonding theory. We'll start by looking at the molecular orbital theory. Like atomic orbitals, when we are talking about molecular orbital, what we're saying are these are electronic wave function of molecules. So atomic orbital, electronic wave function for atoms. Molecular orbital are electronic wave function for molecules. So we can solve these wave function for molecules like H2 plus that only have one electron. So these are things we can solve in exact. So molecular orbitals, again, they are wave functions of molecules. When we're saying they're wave functions, or we're saying they're just wave, probability wave, one of the inherent behavior of any wave in physics, if you think about it, is that waves can interfere with each other. So whenever two waves passes through the same space at the same time, they will interfere with each other in two different ways. Whenever your wave is passing through the space at in phase to each other, so this in phase means we have the peak of one wave meet the peak of the other wave. So say these are the peak of the top wave and the bottom wave, they match up with each other. The crest also match up with each other. So the result of that interference, this is called a constructive interference. Right, so the peak meets the peak, the bottom meets the bottom. And the fact of that constructive interference is we have an increased intensity, or your wave becomes bigger with larger amplitude. Alternatively, it is very easy to imagine your wave can also interfere with each other in a distractive fashion. Means that now your peak and the trough, or the low point and the high points, now meet each other. So in this case, if we're talking about a destructive interference where your waves are out of phase, means they meet each other in different phases. Now what we have is decreased intensity. All right, so these are just very quick, I wouldn't say common sense, but the general behavior of any wave you have in mind. So now let's come to the molecular orbital theory. Well, we're saying molecular orbitals, they are the exact electronic wave function of molecules. Yes, we can calculate the molecular orbitals using quantum mechanics calculation, but you don't want to do that for every molecule you can think about. That's impractical. So when we're talking about molecular orbital theory, normally in organic chemistry, we're talking about something called the LCAO-MO, or in the other word, we're using the linear combination of atomic orbitals to estimate what the shape of your molecular orbital looks like. So this is the LCAO-MO theory. So LCAO-MO, that's linear combination of atomic orbitals to give you an estimate on what your actual atomic orbital looks like. And remember, as long as you have the electronic wave function, as long as you have the molecular orbital, you should have information about what the energy level is and what's the probability in finding the electron in space, right? So they work the same way. So let's use H2 as an example and see how does LCAO-MO work in real life. So look at two different scenarios. The first scenario is now assuming we have hydrogen atom A and hydrogen atom B. And they're like infinitely apart. They don't interact with each other at all. So this RAB tells you the distance between your hydrogen atom A and your hydrogen atom B. And we know hydrogen atom, the electron is likely located in this 1s atomic orbital. Everything else are empty. So we're just using the 1s here. So these are my 1s atomic orbitals. Let me use the same color. All right, so this means each nuclei is holding its own electron in its 1s atomic orbital. They do not interfere with each other because the distance between A and B is infinitely away from each other. And then the next scenario comes is when this RAB, when the distance between atom A and atom B starts to approach the equilibrium bond length, or RE, so that's our equilibrium bond length. My two waves, my two 1s atomic orbitals, or these electronic wave functions, will start to overlap and interfere with each other. Like what we were saying, like any wave, these wave functions, these atomic orbital will interfere in two different fashions. One is a constructive fashion, the other being a destructive fashion. So what does that constructive and destructive interference mean when we're looking at these atomic orbitals? So here, what we have in the constructive interference, remember constructive interference, we're talking about the wave being in phase with each other means they have the same peak meet peak, crest meet crest. So that means they're shaded in the same way. Again, so now we have a new LCAO-MO. So each of the circle is an atomic orbital. And this entire thing here is our LCAO-MO that we created. It is constructed by two 1s atomic orbitals. So this is a sigma bond here, or a sigma MO here. And in the sigma MO, what we have is electron density in between atoms. So if you take this wave function, you do the square of it, you'll see a large probability in between the two atoms. So this is our bonding MO because we have electron density in between atoms. So the bonding MO is a result of constructive interference or constructive linear addition of two atomic orbitals. Alternatively, we could also have these two MO interfere with each other in a destructive fashion. So when we say destructive, what we have are two atomic orbitals that are not in phase with each other. Or they are shaded differently. So one of them is shaded, the other is not. And whenever that happens, in the middle, we have something called a node plane. The node plane works similarly like the node plane in your p atomic orbital. Is whenever you have a node plane, what it means is your wave function changes its sign. So here, the wave function changes its sign from shaded to unshaded, and consequently, there exists a node plane in between the two hydrogen atoms. And because we know the wave function equals to 0 at the node, and anything that's around the node plane will be low electron density regions. So if we're thinking about chemical bonds, whenever you have destructive interference, you'll have a node plane in between the atoms, and consequently, you have low electron density region in between the atoms. So that's why we create anti-bonding MO from the destructive interference of two atomic orbitals. All right, so any two atomic orbitals gives you two molecular orbitals. We don't create or destroy orbitals just randomly. You start from two atomic orbitals, you end up with two molecular orbitals. One being bonding, one being anti-bonding. The bonding one comes from the constructive interference, the anti-bonding one coming from the destructive interference. The MO theory tells us a little bit more about the energy of a chemical bond. So if we look at the correlation diagram or the energy level diagram with the LCAO MO. So what we have, again, is we start from atomic orbitals of hydrogen. So these atomic orbitals all have the spherical shape. A single atom, we don't care if it's shaded or not shaded, it can be either way. But when it starts to form molecular orbitals, if it is undergo a constructive interference, means your atomic orbitals are in phase with each other, what we're having is a constructive interference or a bonding MO. At the same time, it forms an anti-bonding MO where there is a node in between the atoms. And that is our anti-bonding MO. We denote it with a star on that molecular orbital. And now we have the energy of my new molecular orbital. We're ready to put the electrons in to this correlation diagram. And the way to do it is we first start with two neutral hydrogen atoms, each with one electron. And then these electrons go into your molecular orbital. Like what we do with electron configuration, you fill it out with the lowest energy molecular orbital. So we have a total of 2 electrons. So they both end up in my sigma 1s molecular orbital. It can be very helpful if you think about it. One of the ways to use these, we have 2 major ways to use this correlation diagram in organic chemistry. The first one is to use it to just read, are all my electrons in my molecular orbital paired up? If they're all paired up, that's a diamagnetic. If you have singly occupied molecular orbital, those are paramagnetic. The other way to use it is to use the molecular orbital to derive the bond order of a specific atom. So in this case, for example, we have the bond order equals to 1/2 times electron in the bonding MO minus electron in the anti-bonding MO. So in my bonding MO, what we're saying is electrons in my sigma 1s molecular orbital, and the anti-bonding MO is electrons in my sigma 1s star. Whenever you see a star, that is a anti-bonding MO. So for hydrogen H2, we can quickly do that calculation and get a bond order equals to 1/2 times 2 minus 0 to be 1. So it's telling you hydrogen atom has a single bond in between them. I'm just showing hydrogen as a simple example. You can also do that with p-block elements like carbon, nitrogen, oxygen, etc. So you'll probably do that in, well, either your next discussion worksheet or somewhere on our Canvas assignment. Is going back to our original question. Why is O2 a paramagnetic molecule? And LCMO theory can give you a very good answer in why oxygen O2 is a paramagnetic molecule. All right, one last thing and then we'll stop for some questions. The last thing here is we say that LCAO-MO is very useful because we would all talk about diatomic molecules like H2, O2, N2, etc. But in organic chemistry, we rarely use LCAO-MO to talk about the sigma bonds in between atoms, and here is why. So in the LCAO-MO, electrons are fully delocalized over the entire molecule. So this is not on the test, but I just want to show you why people do not use LCAO-MO to describe sigma bonds. So what I'm showing here is the CH3 cation. It is a carbocation, means we have a positive charge located on the carbon. And in the LCAO-MO, what we have are these bottom 3 are my lowest occupied molecular orbitals, or we expect electron density to be around it. But in the LCAO-MO, we don't see that carbon-hydrogen single bond. Rather, the electron density is just fully delocalized over the entire molecule. So the result here is we don't know where exactly is your single bond. It can be very hard to just picture what that atom, what that molecule looks like using pure LCAO-MO. LCAO-MO, on the other hand, gives you very good description on the energy level. So people use it, but seldom use it to describe just pure single bond and to answer the question in where the electrons are. Nevertheless, this is a little bit of the extra. What I want you to know is what is behind LCAO-MO, how to draw these energy level diagrams, and how to use the energy level diagram to get information about a given chemical bond. All right. I'll stop here for questions. Yes.
So with H2, because it's going to use like outer lake shell with just 2 electrons, I guess that's big. So would you never see an anti-bonding molecular orbital?
So the question here is, do you never see an anti-bonding molecular orbital? And the answer is no. So for example, we're using H2 here since we already have the correlation diagram. Let's imagine a hypothetical molecule of H2 minus. And now in total, we have 3 electrons. We need to populate one of the anti-bonding molecular orbital. the result of that populating that anti-bonding molecular orbital, let me just use a different color so we don't mess it up. Assuming now we have this additional green electron that's occupying that anti-bonding molecular orbital, our new bond order of this H2 minus will be 1/2 times 2 minus 1, this 1 coming from this electron in the anti-bonding MO. And we end up with a smaller bond order or a much weaker bond. So it depends on how many electrons you have. We just fill in the molecular orbitals from bottom up. Yes?
Could you explain like what the shading means, like how it's half shaded for the
Mm-hmm. So the question is, what does the shading mean? So the shading here just basically, again, it is a wave. So the shading just tells you whether this wave is a positive number or a negative number. So in this case, it depends on whether or not you have a positive meets positive or positive meets negative. You can have a constructive interference or a destructive interference. So it's more or less for these single atomic orbitals, the shading doesn't matter. It can be all shaded, it can be all left blank, it can be one shaded, one not. It doesn't matter for single atomic orbitals. But once you start to make chemical bond in your molecular orbital, then the shading becomes important. So bonding MO always have the shading match up to form that chemical bond, and anti-bonding always have the shading just out of phase. So they're like having a node in between. Yes?
For H2 minus, would the extra electron also go on the outside? Like, now there's 2 lines on the outside, would it go?
Right, so the question is, where does that electron comes from? So the quick answer is, it can be coming from left or coming from right. I'm just randomly saying it's one of it. But yeah, thank you for pointing that out. Okay, one more question, one last one.
With the bonding orbital,
Mhm.
that means that we can find the electron density cloud, like in between the two, right?
Right.
So where would we find, like what would the electron density cloud look like with the anti-bonding?
So the question here is, imagine you have bonding MO and the anti-bonding MO. Where are the electron densities? So let me just start something new here. Let's work on something else. Instead of S orbital, let's look at a P atomic orbital. So imagine now we have a P atomic orbital interacting with another P atomic orbital. So this is our bonding MO. Right, it's pointing towards each other. It's likely to be our sigma 2pz, for example. So in this case, our electron density is again in between in the bonds. But if we have an anti-bonding MO, what we have is the same join, but now these are what we expect. And it looks like just a single node plane, and you were like, oh, where the electrons are. So, but when you're drawing it out, because of that node plane, what we actually have is something like this, with a very small lobe and a very big lobe. So if we think about this is atom A, this is atom B, so in between atom A and B, we only have very low electron density or very low probability in finding an electron in that space. Or if we're talking about the S orbital, that's the same idea for that one. I don't have enough space, so let me just point out. So what we expect is something like, so this is A, B, and in between we have the node, and then now our anti-bonding will have a very weird shape of something like this. And then in between, anything surrounding that node plane will be very low probability. All right, so let's move on to talk about a different theory. So LCAO-MO, like what we just said, it is great to tell you energy levels of your bonding MO and your anti-bonding MO. You can get information about like highest occupied molecular orbital or HOMO, lowest unoccupied molecular orbital or LUMO. We talk about that in organic chemistry. But its problem is that LCAO-MO really gives you delocalized electron density, or it doesn't tell you where your electron density is localized in your sigma bond, especially when you have more than 2 atoms bonded together. So that's why in organic chemistry, the other quantum bonding theory we use a lot, it's called valence bond theory. So valence bond theory is a fundamentally different quantum mechanics bonding theory comparing to LCAO-MO. They're both quantum mechanics, but in LCAO-MO, we're taking the addition or linear combination of your atomic orbitals. In valence bond theory, what we're talking about is a product of two different atomic orbitals. So since we're talking about product, we're trying to use the valence bond theory to mimic the electron density map. So it tells you a more localized picture of your chemical bond. Or the other way to think about it is it's the same idea. Well, we're imagining a situation where your hydrogen atom A and hydrogen atom B approach each other. What we're talking about using valence bond theory is a product of all the singly occupied atomic orbital will form a chemical bond. So in this case, both HA and HB have a singly occupied 1s atomic orbital. The product of these 1s atomic orbital gives you a chemical bond in valence bond theory. And in valence bond theory, the fundamental idea here is when we are making a chemical bond, the electron between these atoms becomes indistinguishable. Like we no longer know which electron comes from which atom, and they're localized in between the chemical bonds. Let's look at an example. I mean, this is a little bit too theoretical for our taste as organic chemists. So use F2 as an example. What does that mean? So here are the electron configuration of a F atom. So each fluorine would have the electron configuration of helium 2, 2p5, with one singly occupied 2p atomic orbitals. And conventionally, we use 2pz to make sigma bonds when we're talking about organic molecules. And we can sketch out the electron density of these new chemical bonds that's formed by 2pz atomic orbitals. So this is a pz atomic orbital we're talking about. And now we're talking about the product of these two atomic orbitals. So they're all shaded. I mean, it's a product. We don't have linear addition. We don't have nodes anymore. It's a product of two wave function. And we end up with a sketching showing up here. It's basically overlying two atomic orbital. They're all shaded to give you the electron density in that F2 bonds. So the take-home message here is valence bond theory takes products of singly occupied atomic orbital to form a chemical bond. The requirement for a chemical bond formation is one, it must come from singly occupied atomic orbital, and two, these atomic orbital must have big overlap with each other. Like in this case, the two p atomic orbitals are pointing directly towards each other. They have big overlap. All right, so far so good. We want singly occupied atomic orbital to form a chemical bond using valence bond theory. But there is an apparent problem when we're dealing with molecules with more than two atoms. So then we need to introduce the idea of hybridization. So before we start doing that, let's use beryllium H2 as an example to see some problem that's coming from valence bond theory without hybridization. So using beryllium H2 as an example, the electron configuration of beryllium is 1s2, 2s2, so that 1s2 is valence, we don't care about it. And we have 2s2. It's making two sigma bonds with two hydrogen atoms to form a linear molecule. So using the VSEPR, we're expecting to have molecular geometry of beryllium-2 to be a linear molecule like that. And there are apparently two problems of using valence bond theory to describe chemical bonds in beryllium hydride, or BeH2. One of the obvious questions is we have no unpaired electron in beryllium. we only have 2 electrons in the 2s atomic orbital, and using pure valence bond theory, it's predicting no bond formation at all. That's problem number 1. Problem number 2, we're talking about a chemical bond between a 2s atomic orbital and a 1s atomic orbital of hydrogen. And these 2 atomic orbitals are expected to have very small overlap with each other. So let's write out that linear geometry again. And my beryllium would have a 2s atomic orbital, and it's trying to interact with the 1s of the 2 hydrogen atom. And apparently there's just only very small overlap. And we're not happy in both ways. To make things worse, is obviously one can think about the 2pz atomic orbital of beryllium that can potentially overlap with both of the 1s atomic orbitals. So if you think about it, the beryllium 2pz can interact with 1s of hydrogen pretty nicely. It's pointing directly towards it. But then the problem here is the beryllium 2pz doesn't have any electron. So using pure valence bond theory, it's just not gonna work. In order to solve the problem, we came to introduce the promotion and hybridization theory coming from Pauling, which is a very clever solution to all 3 problems we mentioned before. So let's just go over what that hybridization and promotion and hybridization theory is, and we'll see how to use it in organic chemistry. Some theoretical background here. The idea of the promotion and hybridization is that they're assuming in the ground state of beryllium, you can promote one of the electrons from the 2s, W-occupied 2s atomic orbital to the 2pz atomic orbital. So now both of them are singly occupied. This is called a hypothetical excited state. It's not a real excited state. But in order for that to take place, it needs to sacrifice some promotion energy. So that's the energy difference between the 2s and the 2p atomic orbitals. And then the second step here is that hybridization of the atomic orbitals will give you an energy level that's in between your s and p atomic orbitals. And that hybridization minimizes the promotion energy. So instead of going from 2s to these 2p atomic orbital, now by mixing the s and p atomic orbital, we're having the hybridized atomic orbital, and the energy difference between the 2s and your hybridized atomic orbital now becomes much smaller. So let's just see how we use the hybridization theory to help us understand the chemical bond in beryllium hydride, or BeH2. So here are some of the shapes of our hybridized atomic orbitals. When we're doing hybridization, it sounds scary, but what we're essentially doing is just overlay your 2s and 2p atomic orbitals together. So what we have here, the 2s atomic orbital is always just one shade. We don't have different shades for the 2s atomic orbital. It has no angular note. But for the 2p atomic orbital, you have 2 different ways to shade them. Right? We're mixing the 2s with the 2p. And for the 2p, you have 2 possible shading. So in this case, that's the red and the blue, or the blue and red. So depending on how that shading is, you end up with 2 sp orbital, hybridized atomic orbital, that have different directions. All right, so what we're doing here in making that hybridized atomic orbital is just putting the 2s and the 2p on top of each other, and then shade your 2p accordingly. You have 2 different ways to shade it. And then you create 2 different types of hybridized atomic orbital. With the hybridized sp atomic orbital in hand, we can then move on to explain bonding in beryllium hydride, or BeH2. So what it means is after the hybridization, now we have two singly occupied sp atomic orbitals. And both of them, well, two of them will have different shape depending on how you shape that p atomic orbital. So the origin of this sketching coming from previous page, where we'll just overlay the 2s and 2p of the beryllium atomic orbitals. And again, what this sp means is that hybridized atomic orbital comes from one s atomic orbital and another one p atomic orbital. Now we have these sp atomic orbitals, and they are both singly occupied. They're pointing correctly towards the hydrogen atom. We can use that valence bond theory again to describe chemical bonds. So this is what we have. So in beryllium hydride, we have the beryllium interacting with the left hydrogen with one of its hybridized atomic orbital, interact with the right hydrogen with another of its hybridized atomic orbital. It's valence bond theory, so it's electron density. We don't need to shade it. And then let's just move things around. So that's the left one. And that is our right one. So something like that. Let's just superimpose. That's literally superimpose because I'm dragging these orbitals around. All right. So I left some more example in how to draw and how to use the sp2 hybridized atomic orbital and sp3 hybridized atomic orbital. So the idea is the same. For the sp2 atomic orbital, we're mixing that with one s atomic orbital and two p atomic orbital. So sp2 tells you the constitution of that hybridized atomic orbital. The shape of this hybridized atomic orbital coming from overlying your p atomic orbital over the s atomic orbital to give you different shapes of your hybridized atomic orbital. Okay, you might want to mute your phone in the future, but okay. That's for the sp2 hybridized atomic orbital. Typically, we observe that with trigonal planar geometry. So one easy way to get an idea about what hybridization is you check the steric number of the atom of interest. Steric number equals to 2, that's sp. Steric number equals to 3, that's hinting sp2. Steric number equals to 4, that's hinting sp3. So I'll skip this part and you can feel free to check it yourself. The logic is all the same. It's how you mix and match different atomic orbitals to create hybridized atomic orbitals and use it in different molecules with different steric number. But I want to spend our last 10 minutes talking about hybridization in organic molecules. So in this case, we're talking about alkyl groups or ethane, and then alkenes and alkynes. So single carbon-carbon bond, double carbon-carbon bond, and triple carbon-carbon bond. Because we're organic chemists after all, we love carbon and hydrogen. So here, let's get started with the all single bond scenario, or ethane, C2H6. So CH3, CH3. For both carbon center, we have steric number equals to 3. The way to count the steric number, you just count how many of the carbon atom is, how many of that group is surrounding that single carbon atom. So in this case, again, a quick review on the VSEPR. We have carbon, single bonded to carbon, and we have hydrogen, hydrogen, hydrogen. Likewise here, we have the wedge and dash. So that wedge and dash just tells you whether that hydrogen is pointing out towards you or going away from you. And each of the distance here, the bond angle here will be around 109.5 degrees for a tetrahedral geometry. So because Sn equals to 4, what we can derive is that both carbon atoms are sp3 hybridized. So that sp3 orbital comes from one s atomic orbital and mixing 3p atomic orbital with it. What I want you to be able to do is to sketch these chemical bonds coming from the hybridized atomic orbitals using valence bond theory. So the way we do it is we first write out the molecular skeleton, and then we write out our sigma bond between the carbon and the carbon atom. So naturally, there should be a small note on the back, but if you don't draw it, that's also okay. So this is our sigma bond in between the sp3 of left carbon and sp3 of the right carbon. And you also have these sp3 atomic orbitals making chemical bonds with the hydrogen. So each of these small dots is our 1s of hydrogen. So sp3 of carbon forming a sigma bond with 1s of hydrogen. Likewise, we have that for this part. So each of these small circles is a 1s of hydrogen atom. All right, so that's a single bond. This should be straightforward. You have the sp3 hybridized atomic orbitals making all sigma bonds either with its neighboring carbon or with the hydrogen atom. And now let's move on to talk about double bonds. So what does the electron looks like in a double bond and in a triple bond? So now it becomes interesting, and we'll start by talking about pi clouds when we talk about organic reaction. So let's use alkene as an example. So that's an ethane, saying like we have a double bond here. And to answer some of your questions, I'm not gonna test your ability on nomenclature, means I'm not gonna test you on what the name of this molecule is, but you will need it in your standardized test. So what I will do is I'll keep talking about the name of these organic molecules so you're familiar with it. Our tests are an open book. I can't test nomenclature on these. Okay, nevertheless, now we have ethane. And again, we follow the same logic. You first derive what is the steric number of each of the carbon. And here, each of the carbon have 3 things around it. So we have Sn equals to 3. Both carbon are trigonoplanar. You get that by doing the VSEPR. And again, as a reminder, what that means is the bond length here is about 120 degrees. And steric number equals to 3, both of my carbon atoms are sp2 hybridized. So 1s and 2p atomic orbitals mixed together to form your sp2 hybridized atomic orbitals. And now let's sketch it. What does it look like? So first let's sketch the hybridized atomic orbitals. So like this, making a single bond, and then sigma bond between the hydrogen. So if I were to label it out, we have one sigma bond between the sp2 of carbon and sp2 of carbon. We have the sigma bond between sp2 of carbon and 1s of hydrogen. So each here is a hydrogen. But on top of all these sigma bonds, we have a p atomic orbital that is also singly occupied. So if we write out the electron configuration, what we have is sp2, 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 and then we have a leftover p atomic orbitals, and they're all singly occupied. So what that means is you'll have a leftover p atomic orbital pair to make chemical bonds with each other. So what we're having here is we have one pi bond that's formed by overlapping your p atomic orbital on both carbon to form that one single pi bond. So one of the common misunderstanding of pi bond is it exists both above and below your sigma bond. So this is what I like to show. It's the same idea. If we don't draw out all the sigma bond, we only draw the pi bond. We have the p atomic orbital on left carbon. We have the p atomic orbital on right carbon. So what we have is in this burger, if this burger is our chemical bond, our burger in the middle, so these are my sigma bonds. And then both pieces of bread, both on top and below, they are our pi bonds. All right, so that's one common misunderstanding you want to settle ahead of time. Is your pi bond is both above and below your sigma bond. And one last thing, this one is a little nice practice. You can do it yourself. It's instead of just carbon, now we have oxygen with lone pair. You can practice doing valence bond theory and hybridization on that. And one last thing we can try is doing hybridization and also triple bonds. So again, we're following the same logic. You first derive what is the steric number around each carbon. So in both cases, the carbon has steric number equals to 2. So they're linear geometry with sp hybridization. So sp and with 2 singly occupied p atomic orbitals. So they're looking like that. And we can sketch the chemical bonding of ethane, which is a triple bond, by doing what we have here. Carbon, single bond to carbon via the sp atomic orbital, single bond to hydrogen via our sp atomic orbital again. So in both cases, that's our sigma sp, sp. And at the end, that's our sigma sps with hydrogen. And now we have two sets of p atomic orbitals. The first set is like what we showed before. So this red one is like our burger that's on top and below. You have two pieces of bread on top and below of that beef patty. So that's our first pair of pi bond. Let's say that's px, px. But on top of that px, px, you have another pair of the p atomic orbital that's perpendicular to that atomic orbital. So the triple bond means you have an additional pi cloud that's perpendicular to that red one. So if you think about a food item, it's more like you have a burger, and then somehow you have two pieces of additional taco or something that's outside that burger. I really want to find a food item. So far, I haven't got any success. But this one is our second pi bond between py and py atomic orbitals. All right, so that's the end of today. We'll take any questions you may have.